Hello, everyone. I'm Del Pearson with Microwave Journal. I'd like to welcome you to the next installment of our Technical Education webinar series. This webinar is entitled Next Generation AI-Ready RF Circuit Simulation and Optimization for 6G, Wireless, and Aerospace-Defense Designs. It's sponsored by Keysight. Today's presentation will be given to us by Cedric Pujol, an RF Simulation R&D Manager at Keysight. During this webinar, we'll learn about Keysight's new RF simulation professional, Nexus. This educational webinar shows how the next generation of AI-ready RF circuit simulation and optimization workflow can be efficiently and cost-effectively deployed to achieve an unprecedented increase in design productivity and eliminate wasteful tape-out respins. We're going to learn about industry trends driving integration, the workflow-based and Python-enabled user interface that works across a variety of platforms, thorough multi-spec performance characterization. We'll learn to optimize multi-performance specs. We'll use AI-integrated Python automation and integration, and learn about Keysight's cost-effective and flexible licensing. I'm looking forward to it. Now let me introduce our speaker. Cedric Pujol received his BSEE at the Grenoble Institute of Technology in 1997. He worked for 7 years at STM Microelectronics as an R&D engineer. He also developed his skills on silicon RFIC through various positions, including design kit developer for analog and RF, design tool strategy, and customer support. Cedric joined Expedion as an application engineer for Golden Gate, and at Keysight, Cedric is now responsible for RF simulation and optimization. And with that, I will turn it over to him.
Welcome everyone, I'm Cedric from Keysight, and thank you for joining today's webinar titled Next Generation AI-Ready RF Circuit Simulation and Optimization for 6G, Wireless, and Aerospace-Defense Designs. A bit of a mouthful, but I promise it's worth it. Here's a quick look at what we'll be covering today. We'll start by looking at key market trends shaping the future of RF circuit design and simulation. Then, I'll introduce you to RF circuit simulation professional nicknamed Nexus, our new RF circuit simulator designed to meet these evolving demands. Next, we'll explore how we are revamping RF circuit optimization to better handle today's increasingly complex challenges. We'll also show how Nexus is AI-ready and integrates seamlessly into a Python-based ecosystem, enabling smarter workflows and faster innovation. And finally, we'll wrap up with some key takeaways and next steps. To help you get a real feel for Nexus, I'll be using a mix of slides, live demos, and embedded videos throughout the whole presentation. So let's dive right in. As RF design moves into the sub-terahertz and sub-millimeter wave domains, we gain access to massive bandwidth and faster data rates. At the same time, engineers like you face tougher challenges. At these frequencies, electromagnetic behavior becomes more complex, thermal margins tighten, and integration across domains like system architecture, RF design, thermal design is critical. To meet performance demands in smaller footprints, the industry is rapidly adopting 3D heterogeneous integration, or 3D-HI, that you can see an example on this picture. This method combines RFICs, MMICs, advanced packaging techniques, and PCBs, often coming from multiple design flows. This enables compact, high-functionality systems, but also makes design, simulation, and validation much more difficult. As integration density increases, parasitic effects, coupling, and instability risks also grow. Electrothermal interactions impact both performance and reliability, especially in systems like satellites where physical access is not possible. Designers must now meet multiple targets, including gain, stability, EVM, XLR, and thermal safety. They also need to comply with evolving 5G and 6G standards. This requires multi-domain simulation and large-scale optimization across electrical, thermal, and mechanical domains. Traditional methods often fall short. This is where intelligent automation and workflow orchestration can make a real difference, because these challenges are not just technical. They affect how teams work. To meet today's design requirements, engineers often rely on multiple disconnected tools, which adds complexity, increases the chance of errors, and slows down development cycles. To better understand this reality, let's look at what designers themselves are saying. As you can read on that chart extracted from a survey Keysight conducted a couple of years ago, a lot of the designers are using multiple tools to design their IPs. 6 out of 10, more than 5 tools. That leads to a common challenge that the image below illustrates clearly. Many high-frequency design teams work in isolated environments. RFICs, MMICs, analog blocks, and PCBs are often developed using different tools, each with their own data formats and workflows. While these workflows work well individually, this fragmentation limits collaboration, complicates reuse, and increases the risk of errors or inconsistencies, especially in complex 3D HI systems. This fragmentation is precisely why we created Nexus. Nexus is an integrated simulation and optimization platform tailored for RF and high-frequency design and simulation, built to unify multiple design environments and streamline complex workflows. Nexus tackled these challenges by providing an integrated, cross-platform environment specifically designed for RF and high-frequency simulation. It unifies disparate tools and workflows into a single platform, enabling teams to collaborate more effectively and streamline their design process. With Nexus, you gain the power to simulate and optimize across domains and design flows without the friction of incompatible data or tool chains. Now that we understand the motivation behind Nexus, let's explore its core innovation, a user interface that seamlessly connects your existing tools and workflows. First, one of the most valuable features of Nexus is its native integration with the industry's leading EDA platforms, Keysight EDA, Cadence Virtuoso, and Synopsys Custom Compiler. The user interface and workflow remain consistent across all 3 environments. This means engineers can work in the tool they prefer while still collaborating smoothly with colleagues using different platforms. It eliminates the need to translate workflows or retrain teams and enables better collaboration between RF, analog, and packaging teams. Nexus is available in 2 complementary forms, mainly for Cadence and Synopsys Custom Compiler. The first form is native integration within Cadence EDA Explorer and Synopsys PrimeWave, allowing teams to adopt Nexus directly in their existing workflows. As you can see in the video below, Nexus can be used with Cadence Virtuoso inside EDA Explorer on the left and Synopsys Custom Compiler inside PrimeWave on the right. You simply switch to the Nexus simulator and use these tools as usual, with no change to your workflows. Simulations run within these platforms. You can check the log files, you can get the Nexus results, even with the Keysight data display if preferred, as shown here in Custom Compiler. The second form is a modern user interface that can be launched from within the same environments and also from Keysight EDA. This interface enhances traditional workflows with dedicated RF-centric tasks, providing advanced capabilities while remaining fully compatible with existing design practices. For ADS users, an important change is that simulations are no longer configured directly on the schematic. Instead, all simulation setup and control happens through the Nexus interface. This approach declutters schematics, keeping them focused on circuit topology, while making simulation parameters and sweeps easier to access, manage, and reuse. It also encourages cleaner design organization and improves overall workflow transparency. Importantly, it helps ensure that designs created for one platform can be reused on others by avoiding platform-specific components used only for simulation. Nexus also offers a flexible solution for creating views that can be generated on one platform, such as Virtuoso, and reused seamlessly in ADS, as you can see in the video below. I created a setup in Virtuoso that I can reuse or modify in ADS and then reuse again in Virtuoso. Same user interface, same views, just a choice of preferred platform. So how does that benefit you? For example, an IC design in Virtuoso on the left can be simulated with the same setup and simulators when the IC is brought into the package in ADS on the right. Or it enables simulation of two ICs, one made with silicon technology within custom compiler, for example, and another made in 3.5 technology using ADS. Nexus is built for seamless integration across major EDA platforms, allowing teams to work in their preferred environments without losing efficiency. By enabling the reuse of views and data across tools, it supports consistent workflows and simplifies collaboration, especially important in error-centric design, where continuity is critical. In short, Nexus unifies simulation and optimization into structured, reusable workflows that reduce setup time, minimize errors, and standardize processes across teams. Now, with this foundation in place, let's explore how Nexus enables powerful multi-domain simulations to provide deeper insights into your designs. Nexus supports electrical, EM, and thermal simulations, enabling comprehensive analysis across all relevant physical domains. For example, the platform can simulate and optimize important circuit-level metrics such as gain, power efficiency, nonlinear stability, as you can see on the image, EVM, and ACLR. Let's focus on two of these in a demo that we believe will be a great addition to your workflows: stability and modulated signal simulation. We'll start with stability. I won't go too deep into why stability is important. There are many methods to help you determine if your design is stable or not. And that is also the problem. Which method should you trust? And which one provides real insights? For several years now, we have introduced the Winslow probes, named after Dr. Tom Winslow, who authored numerous papers on stability. These probes are, of course, part of Nexus, with a new and unique addition from Dr. Winslow papers that I'm sure you'll appreciate. For the demo, I'll go full screen for better clarity, so let's start. Okay, so for the demo, let's analyze this simple circuit. So it's a transistor that is mounted in an amplifier mode, in which we have inserted between the drain and the gate feedback resistor, and we'll sweep the resistor value to see if the design is stable or unstable for different values of this feedback resistor. So let's start Nexus on this design and maximize it. In that case, we'll look at the sweep of this feedback resistor, so 10 values between 200 ohms and 2.2 kilo ohms. So let's run the simulation, and that will use the Kurokawa method of stability and the Nyquist stability criteria as well to detect any potential instability in that design. So that's running all the analysis on 500 stability points, and that detects one unstable frequency, so that's the Kurokawa method, and the Nyquist criteria, so the number of encirclements around the -1,0 point. We see that for one specific value, the lowest value, we get to 1, so there's one encirclement, so the design is unstable, which is basically also what the Kurokawa method gets here with this 6.5-ish frequency being unstable. So that's fine. We know that it's unstable for this specific resistor, stable for the others, but how stable that is. And in Nexus, you can activate the new computation based on Tom Winslow's work on the stability margin, so where you can compute in driving point impedance and admittance the margin that you have for this specific stability. So instead of saying it's just stable or unstable, that will tell you if it's stable and how close you are from an instability. So here we are, the same kind of curves that we have here, except that we have now two more curves, the stability margin for the impedance. And you can see this greenish huge peak that corroborates that's oscillating, that you can see also on that area. But we kind of estimate that above -15 dB, then you're normally pretty safe in terms of stability. That depends on plenty of things, but that should be pretty safe. And you can see that for some other values, though this method are saying it's stable, it's very close to instability. You can see here that you're below that, and some of them are also below that in the admittance version, which means that if you add process impairments, if you add some assembly in the manufacturing, there's a huge possibility that this that looks stable will probably join that curve and be unstable. So that gives you a quality of the stability. In Nexus, you can now get this kind of subtlety between stable or unstable. It's stable, but then probably that needs to be optimized to get more margin to avoid any process impairment that you can have, and making your design finally unstable instead of stable. Now that we have covered stability, one of the other gems in Nexus is the virtual test benches, which let you see how a device reacts under real-life signals. Why is this more beneficial than classical IP3 or IPN tests? Two answers. First, EVM is one of the key figures of merit in all documents, datasheets, wireless standards requirements. Also, as you can see on the right, EVM depends on a lot of factors that continuous wave signals cannot really catch without large approximations that often lead to over-design. The second answer is visual. A modulated waveform is not just a couple of sine waves. I think the picture explains it well. The amplitude swings your design faces are vastly larger than what IP3 or IP5 tests try to mimic. Latest modulation standards have peak-to-average power ratios greater than 15 dB. Yes, 15. Better to avoid approximations. Within Nexus, you can embed this test seamlessly and quickly get the system metrics you need to focus on and even optimize, exactly as if you were plugging Keysight instruments inside your design platform with the same fidelity as the code is leveraged from our own instruments. I'll now switch to show you how this works in real life in Nexus. So for this demo around modulated signals using virtual test benches in Nexus, we will use a power amplifier that operates around 2 GHz, in which we will replace virtually this RF input, which is a classical continuous wave input, with a WLAN and a 5G signal, and look at the data here at VLOAD, and in which we will compute the EVM, the spectrum, and the constellation without touching the schematic. So to do this in Nexus, we will run envelope simulations. Envelope is the only algorithm that can handle complex signals, and modulated signals are complex. So we will look at the 5G one and edit the 5G. So you see that you have a lot more than just WLAN and 5G. There are a lot of waveforms that you can use. The way to connect the Nexus UI to the schematic is through this UI, where you say which source you will overwrite, so my RF in, and looking at the VLOAD here. So it's basically like if you were putting, instead of RF in, a Keysight source, here a 5G one, and if you were putting or plugging inside the schematic at the VLOAD node, Keysight spectral analyzer, that would be equivalent because we leverage the code between the software and the hardware. So you can change as many parameters as you want for this standard. The only things that have changed here are basically the input and the output frequency, and the input power, that are the variables that I'm using in Nexus, and also put the modulation to be here, in that case, a 64 QAM modulation, but that's all. So I use the same input and output. You can use different if you're not using something like a PF for my case. So if you're using a transmitter or a receiver, you can of course differentiate that. So if I'm validating these two, I will run the two simulations, WLAN and 5G. WLAN is set up the same. So we are launching System View, our Keysight system simulator in the background. It's embedded in Nexus, so you don't need an external installation for this. It's already there. And then at the output of these two simulations, we will look at the performances that I've defined, so an EVM and a spectrum, of course, for each analysis. So here's the one for the WLAN and the 5G. So the data frame is a little bit longer, but should come anytime soon. So you see it's okay, too quick. almost 13% here with a spectrum that is a bit noisy. And for 5G, it's 10, which is a little bit cleaner. 10 and 13%, so that means that it's very difficult to say we have one EVM simulation, so that corroborates the slides that I was showing about that it's very dependent. And if you're using an IP3 or IP5, even IP9 computation, then it's an approximation of all these values that can range quite widely depending on the type of modulation that you will put inside your circuit. Of course, it's a performance, as I mentioned. So if it's a performance, you can sweep it, you can optimize it. Here, I did that for DC, S parameter, and the envelope at the same time to get better performances. If you have corners, you can do that on corners as well. That's working. But you can also see more than the 3 figures of merit that I've shown, like the spectrum and the EVM. So here's the constellation, by the way, that have been computed. So the constellation that's the WLAN and that's the 5G. So the 64 QAM and the QPS, the 16 QAM for the WLAN here. But of course, you can see much more than this if you want. System View computes a lot more data that you are seeing here. So you can use this one and optimize or simulate anything that System View has stored. The EVM that I was using is just an example. So that's a very quick demonstration of what we can do for modulated signals inside Nexus. And I will now switch back to the slides. On top of these nominal simulations, Nexus can also incorporate environmental and layout-aware conditions, such as IC-EM interactions, where Nexus can co-simulate and co-optimize with EM views generated by Keysight RF Pro, package and board level EM interactions to test the IP against manufacturing variations, or self-healing, which you can see running in this embedded video. For this case, we're looking at an operational amplifier created in Cadence Virtuoso, on which we want to compute the electrothermal profile induced by the layout. Nexus and its thermal solver are feeding themselves internally with the impact of the current operating point on the temperature rise, which then gives a new operating point, then a new temperature profile. It reaches a step where it stabilizes, and then you can assess the impact on the circuit of the current layout and see how the temperature repartition looks like in 2D or 3D over the different substrate and metal layers. But capturing these detailed effects is only part of the story. The real challenge lies in optimizing multiple, often competing performances targets simultaneously across these domains. That's where Nexus advanced parallel optimization architecture comes into play. Nexus algorithms are designed to handle today's complex RF requirements, where multiple interdependent metrics must be optimized across wide frequency ranges and diverse signal types. Consider multi-band filters, for example, as you can see on that PA front end on the picture. These components need to perform well across adjacent frequency bands without causing interference. Optimizing them individually can degrade overall system performance. Nexus simulates these interactions comprehensively, ensuring robust operation across the entire spectrum. Beyond standard metrics like gain or insertion loss, modern wireless systems require evaluation of modulation-specific parameters, such as EVM and ACLR, as already discussed. 5G and emerging 6G standards demand hyper-tight control over spectral purity, linearity, and signal integrity. Using IP3 approximations can make the optimizations harder to achieve due to the margins taken. Optimizing directly EVM would probably help balance the trade-offs better without over-designing. Naturally, optimizing all these aspects creates a vast and complex design space. On the left, you see a stylized loss surface illustrating what optimization looks like internally. Each particle represents a population navigating the landscape of optimization, encountering local minima, saddle points, and flat regions. This visualization helps explain the difficulty of optimization in high-dimensional spaces. On the right, a more conventional contour plot describing all the potential local minima that an optimizer can get trapped into. To address these challenges, Nexus incorporates advanced algorithms, some local optimizers for speed, if your design is well-centered, some more global that will try to find other combinations better than the current one. These algorithms include a customized version of simulated annealing called Corona, cutting-edge gradient and gradient-free methods, and the highly requested particle swarm optimization. Let's take a quick look how Nexus performs these optimizations in practice. Okay, so for this demo around optimization, we will use a voltage-controlled oscillator as a demo vehicle that is supposed to oscillate at 1.8 GHz at the middle of the tuning range. So if we go to Nexus, I've already pre-canned some analysis and a sweeping task for the tuning range, and also some performances to extract the oscillation frequency and the oscillation amplitude at the middle of the tuning range. And the intent would be to have this oscillation frequency very close to 1.8 GHz while maintaining the oscillation amplitude high enough for the future stages in that chain. So if I'm simulating the nominal simulation, you will see that I'm close to the specs, but not exactly where I want to go. I'm at 1.86 and on 1.8, and the amplitude of the oscillation at this specific frequency is very close to the 230, but it's not at 230. So to optimize this, I can add in the task a new optimization, select all the variables that contribute to the analysis. By default, Nexus add a default 10% range around the nominal value. Then in the analysis, I will use this sweep because I want to be at the middle of the tuning range, and use the two performances that I've already written. I will put a higher weight on the oscillation frequency because this is the one I'm the most interested in. And then after that, I can run the simulation, and you will see the optimization running. So we get a live visualization of the results where you can see in dashed the original, so the baseline, and in solid the best iteration that we have so far. And Nexus already reached the best, at least the targets that we have, with something which is very close to 1.8 and above 230 millivolts as expected. So fairly simple in terms of flow that you can use. The good thing about it is that you can use that in any platform because it's part of the Nexus platform. So that means wherever you're using Nexus, that will be available, and you can use this kind of optimization or all the kind of tools that you are using in your workflow. Critically, Nexus leverages parallel computing to speed up this inherently complex optimization process, enabling up to 16 times faster convergence. This means you can explore multiple design trade-offs and iterations quickly, get deeper insight into performance bottlenecks, and reduce your overall design cycle time. On your screen, you can see how Nexus handles the parallelism. It's a power amplifier example where we optimize the DC performance, the nonlinear characteristics like AM/AM and AM/PM, in 3 regions: linear, compression, and 6 dB back off from compression. If you launch a nominal simulations, I sped up the optimization part for time constraints. You get the optimization in 1 minute and 30 seconds, but you can now use more solvers, 4 in this example, and let's perform the same optimization. I've also made sure the seed is the same to compare apples to apples. But you can now see the points arrive faster and the overall runtime decrease to 35 seconds. So what can Nexus parallelize? Nearly everything. Circuit solvers, parameter sweeps, frequency plan evaluations, and even populations within evolutionary algorithms like particle swarm optimization. It also supports process corners, both foundry provided and user-defined. As shown in the figure, managing process variations is critical since they can significantly degrade circuit performance. Optimizing solely for nominal conditions risks overlooking the full manufacturing variability. By running the optimizer across all process corners and parallelizing these evaluations, Nexus helps to efficiently identify the optimal variable set that minimizes performance degradation caused by the process impairments. You might be wondering, optimization at this scale requires powerful computational resources, and you're right. What about budget? Rest assured, Nexus is designed with your budget in mind by using a flexible token-based licensing system. For standard analysis, you use regular Nexus tokens, while for parallelism, either from local machines or high-performance computing clusters, you can use cost-effective HPC tokens. This setup lets you allocate resources efficiently and only pay for the computing power you need. This licensing model supports scalability and adaptability, helping teams optimize their workflows while keeping costs under control, making it affordable for teams of all sizes and without requiring large upfront investment. With these optimization capabilities in place, let's explore Nexus' cornerstone feature, Python integration unlocking true AI readiness. Nexus is built around deep Python integration, making it one of the most flexible and extensible design platforms available for RF and high-frequency engineering. And it's not just Nexus. All Keysight EDA tools are embracing this Python transformation to give you access to core capabilities even in a fully headless environment. Why Python? First, it's non-proprietary and that makes your workflows future-proof. Second, it's a powerful, popular language that most new engineers already know. Finally, support is everywhere, from online forums to AI assistants like GitHub Copilot and ChatGPT that are not or rarely trained on proprietary languages. Python enables powerful automation. Full scripting access. Python can drive the GUI of Nexus, run simulations, and orchestrates entire workflows, fully automating design, simulation, and post-processing. Headless operation. You can run Nexus workflows without any GUI interaction, ideal for batch simulations, regression testing, or HPC deployment. Reusable functions. Engineers can write and share Python functions for common tasks, like you can see on this VCO post-processing, replacing brittle scripts with maintainable and scalable tools. And the last one is bring your own optimizers. We will be continuously expanding our optimization capabilities, and we'll soon be adding new algorithms such as CMAES and various AI-based techniques. But a common question we get is, which optimizer should I use? To help with that, we've introduced an auto selection mode. It intelligently chooses an optimizer based on problem characteristics, such as number and type of variables, discrete or continuous, the number of objectives you have in your optimization, and other key parameters. That said, there's no single algorithm that performs best across all use cases. If someone claims otherwise, chances are the testing was limited, perhaps to a single circuit. But the reality is optimization needs do vary widely. For example, an acoustic filter with sharp rejection notches has a very different behavior compared to a power amplifier with a smooth gain curve. Even within PAs, a Class AB design and a Doherty PA present very different challenges. That's why, in addition to offering a robust set of built-in optimizers that cover a broad range of applications, we are giving you the option to bring your own. In Nexus, you can embed your preferred optimizer, whether it's third-party, custom developed, or something that you have found online. As long as it has a Python API, integration is straightforward, with a one-time setup that typically takes less than 15 minutes. Let me show you a bit more in detail how it works. So to demo the integration of third-party optimizers inside Nexus, we will reuse the small VCO example that I had used initially. And instead of using the optimizer, we'll use a third-party one. So I can duplicate the setting that I had, double click here, and in the optimizer, the strategy, instead of the default one in Nexus or any of the list that we are supporting, I will go to Python, and it asks for a script and a function in that script that it should execute to make the optimization. So I have something that is already done here. See, it's fairly small. We're talking about 80 lines of code plus with including documentation. There's a class that you can find in our examples that you can reuse at length, because that will be the same one for almost all the algorithms. That is basically defining or passing the problem that you are currently defining in the GUI to a specific function. So this one here, where we will use an external algorithm to the list that we have in Nexus. So to do this, we will use PyMu, who's the multi-objective optimization library, hence the MU, that has a broad range of evolutionary algorithms, and we will use the NSGA2 that you are seeing here. And that's basically based on an example from PyMu on this one. The only thing that we modified is that the problem that we passed is the Nexus problem that we are seeing in the GUI. So I will copy that script, that is the path, in the setup here, the name of the function, and that's all. So once I've done that, I can launch the simulation here, and that will launch the simulation as if it were one of the native algorithms from Nexus. So you can use any specific algorithm that you have that will basically work. And to show you that it's not difficult, so if I want to use another algorithm, I can here use another one. So I will use NSGA3 this time. So Copilot will help me. So cloning what I had, except that he put NSGA3, and I will show you that it's really not difficult, because if I'm going to the NSGA3 here, there's an example. So I will use their example here, put that inside Nexus more here. So I will keep the logger. And the only thing that I would put is that it's a single objective for this simulation, the population size here. And the problem is the Nexus problem. Done once for all, and now we have NSGA3 that can work exactly the same way. See that started here, and I would stop that one, go here, put NSGA3, and now this time that will use NSGA3. So I've basically in less than a minute put the NSGA3 algorithm from PyMu inside Nexus without any problem. So you can do that on your own pretty easily for any algorithm that you like, either homegrown or as I'm doing here with a public library that you can find in Python. As you just saw, integrating your own optimizers into Nexus is not only straightforward, but it gives you complete control over how optimization is handled into your specific workflow. But we wanted to give you even more flexibility. Nexus is designed to be AI ready through an open and flexible architecture and framework, not only for optimization, but really to empower users to integrate AI capabilities in a way that suits your needs. Since proprietary approaches do not always align with flexibility, Nexus leverages its open Python architecture to give you full transparency and control over your design workflows. On the screen now, you can see an example of this where we drive both ADS and Nexus in a pure headless way. No GUI at all. The intent is to create a step-Z filter layout and schematic that will meet some given specifications. We start from theory and check the results are not really meeting the spec. We can do this by launching Nexus and check with a very simple function returning true or false. In this case, As it's false, we can use Nexus optimizers to meet the specs. After another verification that now matches the specification we had, we can now create a sample report, the final schematic, and a layout in ADS. This very basic Jupyter notebook is only for education, but it shows that you can probably unleash your imagination to create a set of algorithms that would optimize, find new topologies without needing gazillion of mouse clicks. Today, you can connect Nexus to AI agents or large language models to automatically generate and refine design candidates, and on demand, run simulations, analyze results, and intelligently iterate. You also have the freedom to embed your own custom AI or machine learning models for predictive modeling, surrogate modeling, or learned optimization strategies directly within your workflows. Thanks to Python, engineers retain full oversight of AI-driven decisions with the ability to inspect, refine, or override behaviors as needed. Looking ahead, we'll offer turnkey AI-enabled solutions for users who want ready-to-use capabilities, but never without giving up the ability for you to customize them. Whether you prefer a plug-and-play setup or a fully programmable workflow, Nexus adapts to your style. With its Python foundation, Nexus remains future-proof and fully compatible with popular AI frameworks like TensorFlow, Scikit-learn, or PyTorch. Rather than replacing your AI tools, Nexus enhances them, helping you build intelligent and scalable design flows on new terms. In conclusion, today's shift to sub-terahertz frequencies and 3D heterogeneous integration is transforming RF and high-frequency design. These technologies offer major performance gains, but also introduce significant complexity across simulation domains, design tools, and performance targets. Nexus is built to address this. It unifies workflows, automates intelligently, and supports AI-driven strategies to help teams work faster and more effectively. Whether you're optimizing an RF design, co-simulating a 3D HI module, or applying AI to uncover new topologies, Nexus is here to help you and your team stay focused on innovation, not on constantly fighting complexity. As I've just scratched the surface of Nexus capabilities today, if you want to know more about Nexus, please visit the Nexus product page to apply for a free trial. You can also download the Nexus brochure to explore the platform's full range of capabilities and use cases. And if you start with Nexus, most of the examples shown today are available in the Nexus product. So please use them as much as you want to get the feel of it. You can also contact Keysight for details on how to upgrade your RF-microwave-mmWave design environment using Nexus for simulation, optimization, or workflow automation. Finally, that wraps up the main part of today's talk. I'll now take some questions that you have submitted while I was talking. And for anything we don't get to live, we'll be sure to follow up afterward. Thanks again for joining us today. I hope this session sparked some ideas about how Nexus can streamline your workflow and support your team in pushing the boundaries of RF design. And by the way, in case you're attending IMS, the conference this month, be sure to drop by the Keysight booth as depicted below me. I'll be present personally and happy to connect and continue the conversation in person.
Awesome. Thank you, Cedric. That was a great presentation, and you took a lot of my lines right at the end, so we're going to hop into